Welcome to our fourth lecture on fluids and temperature. And you're probably looking at this equation going, OMG, or whatever. Now this one is Bernoulli's principle. In other words, the pressure and everything from one side is constant. You might see this equals a constant. What I did was to expand it out to make it easier for you. Remember, D could be rho. You might see the rho d y and 1/2 rho v squared. But I'm using the d for density instead of the rho. Now, one thing interesting about this equation, depending on what you have, you can eliminate a lot of your variables and make it look very simple. Okay, so if you see something where have a density of a fluid and water moving from one end to the other, and you're actually changing the height. So remember, AV is just everything straight, but on this one, we're going to change the height of our liquid either as a pipe height, or like in this first one, we're going out of an opening. So I'm going to write down the equation. Squared, and there's the second part. Okay, you're probably thinking, okay, there's no pressure. Well, the pressure is equal, so what happens, these actually, if P1 is equal to P2, do you really need them? No. It has, that makes it a lot easier on this, doesn't it? And so I have density. So I'm going to go on and write this down. So that's 1100. Went on and expanded it. G, which is 10. Now you can see the water is at here, and then you have a little opening going out this way. Okay, so it's 2 meters tall. Oh, let me give you a little hint. That almost looks like MGH, potential energy. Technically it is. And this is 1/2 times the density. Okay. And you're thinking, what is the velocity at the top of the belt? Well, is the water moving? No. So that's 0. That almost looks like kinetic energy. Okay, so P, we've already eliminated the P's. Okay, so let's look at it on the other side. And there's 10. Now we're at 0.25 plus 1/2 1100. And we're looking for this second V. Okay, since this is in MKS system, we're going to be in meters per second. You're probably thinking, okay, that's 0, no big deal. Okay, I got 1100. I don't have to do that. This almost looks like a good old conservation of energy equation. And you are exactly right, because Bernoulli deals with conservation of energy. So what you did was just make a very hard-looking problem easier. Now, this one, I'm going to skip this one because it's just like, so we can look at the change of pipe height and do that. So you're looking for your new Y. And just remember, you just need one of the Y's as a reference point. But if you have something like this, where you have two pressures, and there's my equation. Okay, so we have pressure at one end of the pipe, 3.5. So if I gave you if you were given two pressures, you will have to put them in. Okay, the fluid density is 900, and G is 10. Okay, now on this one, it's flowing at a rate. I'm going to leave this blank just for a minute. There's 900, and it's going at 5 meters per second. Don't forget the squared. And let's go for the other side. That's 2.5 times 10 to the 5th, and then that's 900. 10. I'm going to leave that blank, and on this one you notice you can run out of room real quick. Okay, there's 1/2, 900, and there's the v squared. We know that is v in meters per second. Okay, now you're thinking, okay, what do I need to put in here? Okay, so let's see, the pipe is, okay, I got some room here, so the pipe is doing this. So this is here, and this is here. So that's going to be 3 meters. So what you can do, look at column 1 is a reference point. You can say that this is 0, and this is -3. Okay, so you make that 0 and that -3. Or you can say that if this is 0, if my bottom is 0, this is 3. Either one does work. I'm just going to do the first one, so that's 0 and -3 in there. So when you see it drop, make one of the heights before or after a reference point, unless like in the first one you were given the 2 heights, so you couldn't do that way. But if you're saying that it drops or it raises, make one of them 0, which is your reference point, and then adjust your other y accordingly. Okay, that's pretty much it on Bernoulli. So if you see something like this looks crazy, chances are your problem will be a Bernoulli equation. Remember, if you have any questions, feel free to contact me or your